In this video, I want to find the motion of a charge inside the presence of a magnetic field. I will assume that the magnetic field B points in the positive z direction. I have defined my coordinate system in a way where x points out of the board towards u, y points to the right, and if you apply the right hand rule on x and y, you will find that the z direction points up in the same direction as B. Now, anytime that I want to predict the motion, I need to use Newton's second law. This physics principle allows me to predict the motion of my system. Now, when I apply Newton's second law, I need to know what the system is. And in this case, I will choose the system to be just the charge Q. So everything else is part of the surroundings, and this means that the net force acting on my system, in this case there is only one, that will be the magnetic force that the magnetic field exerts on the charge, and this is given by QV cross B. Now, if you wonder, every charge has a mass. If you wonder why don't I take the gravitational force into account here, the reason is why we do this all the time in physics. We take into account the dominant interactions, the dominant forces, and for a charged particle moving in a magnetic field, if you do calculate mg, the mass of the charge times the gravitational constant of the Earth, you will find it to be orders of magnitude smaller than the magnetic force. So, in principle, is it there? Is the gravitational force there? Yes, it is. In practice, does it affect the motion of the particle? No, it doesn't. It is so tiny, it does not make a significant difference. So, the magnetic force is QV cross B. Now, I will show you how to do these calculations. It is a cross product, and to find it, I do need to I'm gonna follow the determinant approach. So it will be a determinant this will be x hat, y hat, z hat. On the second row, I need to use the first vector of the cross product, vx, vy, vz. And on the last row, I will use the second vector of my cross product, b. But I did say that b points in the direction of z. So I have 0, 0, and the z component of the magnetic field, and this is a determinant. Okay, so I do need to calculate this as I do with determinants. So I will say that this is x hat times vy bz, and then minus 0 times vz, which gives me 0. And then I have minus y hat, and it will be vx bz, vx bz minus 0 times vz, so that gives me 0. And then I have plus z hat, 0 times 0, so this will be just 0. Okay, there is no z hat component, and this is the net force that is acting on the charge. Now, I do know from Newton's second law that the net force, it is dp of the system over dt. I will make the assumption that the particle is moving at a speed much less than the speed of light, and this allows me to say that the net force is dv over dt, and this is m times x hat dvx over dt plus y hat dvy over dt plus z hat dvz over dt. Now what I will do, okay, let's call this equation 1, let's call this equation 2, and let's call this equation 3. Now what I'm gonna do, since I know the interactions and I found the net force using the interactions, and I know Newton's second law, which is equation 3, and both equations 2 and 3 are describing the same thing, the net force, one through the interactions and one through Newton's second law. I will use both of them, I will combine them and set them equal to each other to see what I get. Now when I do that, I will see that I will need to set everything that is in the x hat direction, I need to set it equal to each other. Everything from the y hat direction, I need to set it equal to each other, and the same thing in the z hat. So what I will get by setting 2 equals 3, I'm going to get 3 equations, one for x, one for y, and one for z. And I'm going to do that here. So from 2 and 3, I will get, so I have from the x, I get m dvx dt. It's equal to q v vy bz, and then from the y I have m dvy dt equals minus vx, I forgot the q, bz, and then in the z direction I have m dvz over dt equals 0. Now this last one, of course, is the easiest one to solve. If the derivative is 0, that means that your variable is a constant, so vz will be a constant as a function of time. Whatever you had with whatever velocity in the z direction the particle entered the magnetic field, it will continue having the same vz component. Okay, so this is a constant during the motion of the particle inside the magnetic field. Now, let's call 1, 2, 3. So this will be the 4. This will be the 5. I'm gonna rewrite them again here, and I will rearrange them. So to solve this, dvx over dt q bz over m, and those are my constants, times vy. Okay, pay attention here. This is the derivative of vx, but I have on the right side I have vy, and then equation 5 becomes dvy over dt minus q bz over m. The constant is the same, the only difference is the sign, and this is vx. I do want to mention now something important. I have shown you in the past how to solve these simple first order differential equations. Well, not these ones. How to solve first order differential equations by moving everything, separating the variables, one on the left, one on the right, and then integrating. Now there is an issue here. What is time dependent and what is constant? Q, B, Z, M, those are constants. Those do not depend on time. Now Vx, the x component of velocity, does depend on time, and Vy does depend on time, and they are not the same thing. So when you do integrate, since you don't know what Vy is, you cannot really do the integration. It is wrong to simply move Vy on the left side, dt on the right side, and proceed with integration. You cannot do this integration. And the same thing here, these are my constants, and I have Vy as a function of time and Vx as a function of time. I cannot simply move Vx on the left side, dt on the right side, and proceed with integration. Vx and Vy are two different functions of time. That's why I cannot do this integration. Now, to make my life a little bit easier, I will call these constants omega. Okay, just so I have to write less things. And this becomes minus omega Vx. Just so I remember what I defined omega to be, I will write equation here. This will be equation 6, q bz over m. This is my equation 6. Let's call this 7 and this one 8. I will show you an approach that we can use to solve these differential equations together at the same time. So I'm going to write them again here. dv y dt I will define a new quantity, eta, to be Vx plus the imaginary unit Vy. Now, I'm going to take the derivative of this eta with respect to time. And I will have dvx over dt. Since I is a unit, it's a constant. Even though this is a product, when you take the derivative of I with respect to time, you get a 0. So the only term that survives from the product rule is dvy dt. Now this is what I'm gonna do. So I think I had this to be equation 7, and this was equation 8. I will use these two equations here. Equation 7, equation 8. dvx over dt is omega Vy, and I have plus I dvy dt, which is minus omega Vx. I used my differential equations here, and this will give me omega Vy minus I omega Vx. Now what I will do, I will take minus I omega as a common factor, and I took out the omega as a common factor. Now I also took out the minus I. If I multiply I with Vy, then I times I will give me I squared, which is minus 1. With the minus sign will go away. Omega times Vy is the same as omega times Vy, and I took out minus I omega, so that leaves me with Vx. But this is what I defined eta to be, so this is simply minus I times omega eta. This is a very, very convenient result. I will rewrite this as d eta over dt equals minus I omega eta. This is a differential equation that we can actually solve by separating the variables on the two sides. And now I can integrate. I'm gonna say that this goes from 0 to t. I'm gonna change that to a t prime. This goes from eta initial to eta final. I'm gonna change that to prime, and this gives me the natural log of eta prime from eta final to eta initial. This is simply minus I omega t prime from 0 to t, and this is ln eta minus ln eta initial is equal to minus I omega t, and I have ln the fraction eta over eta initial, and this is minus I omega t. So solving for eta, I have eta initial times e to the minus I omega t. Now, I said eta initial because this is the value of eta when the time equals 0. And eta depends on the velocities vx and vy, so whatever vx and vy I had at t equals 0, this is what will determine eta initial. This is the solution, so I'm gonna call this equation 9. This is the solution to the differential equation that I got by using this quantity eta. And it is amazing that I had two differential equations that each one of them was depending on the solution of the other one, but by using this expression, this function, I was able to combine them in one and obtain a much more simple differential equation, which I can solve with a simple approach, relatively simple approach, and I got the solution. Now this will give me the velocities vx and vy as a function of time. But I'm not done yet. I also want to know what is the motion. How does the particle move in terms of its position? How does its position change? Now we know that n depends on the velocity. That's how I defined it. One thing that I can do now, as I usually do, once I have the velocities as a function of time, I move on and I do the integration one more time to find the position. I do want to make a note here that eta essentially contains or includes my solution for velocities for Vx and Vy. Okay, so by finding eta as a function of time, I have the solution for the velocity. And now the next step is to obtain information about position. And what I will do, in the same way that I defined eta, I will follow a similar approach to define the quantity that I call that here with the symbol xi. It has been a while, many years, since I wrote Greek, in Greek, and I think that's how I used to do the letter xi. Okay, I know in the US, Greek letters are called in a different way. Anyway, this is the Greek letter xi, at least my Greek letter xi, and that's how I'm defining this function. Eta was, just to remind you, Vx plus I Vy, and because I know that Vx is dx over dt and Vy is dy over dt, what this means is that eta is dxi over dt. But I did find the solution for eta to be the initial eta times e to the minus I omega t. So I'm gonna use, I think I stopped on equation 9, so let's call this equation 10, and let's go back and see. I think that was, so that was 9. So repeating, this is 9. From 9 and 10, dc over dt equals eta initial e to the minus omega t, and I will dc is equal to eta initial e to the minus omega t dt. I will integrate this from 0 to t, so I'm going to change that symbol to a t prime, and this goes from xi initial, which is related to the initial position of the particle, to xi final, and I will change that to add the prime. So this will give me my xi final minus xi initial. Now eta initial is a constant dependent on the initial velocity of the particle, so it is a constant. And when I integrate e to the minus I omega, I do need to include this e to the minus I omega t prime. That goes from 0 to t, and this is eta initial minus I omega e to the minus I omega t, and when I use a 0 here, I get e to the 0, which is 1. And I do want to avoid having the minus sign in the denominator. One thing I can do, I can multiply both the numerator and the denominator with I. So I will have I times eta initial. Now in the denominator I will have minus I times I minus I squared, but I squared is minus 1, so that cancels out with the minus, and that makes it look much better. And this is, so moving on, xi as a function of time, which depends on the final on the positions, is equal to xi initial, which depends on the initial position. Let's do minus I eta I omega plus e to the minus I omega t, and I'm gonna call this equation 11. And this is, I want to make a note, xi includes the information about the position, so this contains the solution for position. Now I have made the claim that eta and xi contain the solution for position, for velocity and position respectively, but I will not be surprised if you tell me that this is not obvious, and I do want to show you how we can see that. So this is the solution that I found for eta, and I will just use the definition how I defined this quantity, and this will be Vx plus I Vy is equal to Vx initial plus I Vy initial e to the minus I omega t. And I do want to remind you, because I have eta initial here, I am using the initial values of Vx and Vy. Now what I will do, Vx initial times e to the minus I omega t plus I Vy initial e to the minus I omega t. And from this, I conclude Vx initial e to the minus I omega t, and then Vy is Vy initial e to the minus omega t. And there we go. I have the solution for Vx and Vy. And I can do the same thing now with my solution for Xi. And what I had was Xi equals Xi initial. Now I forgot, so I need to go back to my solution. Xi initial, minus I eta initial over omega plus I eta initial over omega e to the minus I omega t. And now I will use the quantities, how I have defined this. So it will be x plus I y equals x initial plus I y initial minus I, and here I have to be careful, this is Vx initial plus I Vy initial over omega plus I Vx initial plus I Vy initial over omega e to the minus I omega t. And actually I'm gonna do x initial, I will do a little bit of work here, plus I y initial minus I Vx initial omega minus I times I will give me minus I squared, or simply plus Vy initial over omega plus I Vxi over omega e to the minus I omega t, and then plus I squared will give me simply minus 1 minus Vy initial over omega e to the minus I omega t. And I'm gonna rearrange some things. X initial plus Vy initial omega minus Vy initial omega e to the minus omega t. Let's call this, put it in bracket, plus I. Now I have y initial, let's see, where do we have, plus I minus Vx initial omega, and then plus Vx initial omega e to the minus omega t. And now I can say x is given by this. And then y is equal to y initial minus Vx initial over omega plus Vx initial over omega e to the minus omega t. And these are the solutions for position. Now it is a little bit more clear that I do have x and y as a function of time. These are constants, and it is interesting to see that I have some constants for x and y, but then I have e to the minus omega t for both of them. And this is showing me that my particle is moving on the xy plane on a circle. Okay, I do have omega t, so the angle, the way that the particle moves on the xy plane does depend on time. And in particular, I know from complex numbers that my particle will move on a circle on the xy plane. Now, because it is moving at a constant z velocity and on a circle on the xy plane, essentially it's moving on a helix. So if you look at it from the z-axis, if you look at it on the xy plane, all you see is a circle. But on the z-axis, it is simply moving with a constant velocity. So that was the solution and the approach for using complex number in solving these differential equations.